Lesson 2, multiplying rational expressions. So write each rational expression as an equivalent rational expression in lowest terms. So when we multiply rational expressions, our overall plan is factor everything and then multiply the two rational expressions together and then simplify like terms. So x squared minus 4, that's x plus 2, x minus 2. That's the difference of perfect squares. X minus 3 is a linear factor. We can't do anything with that. Times what? Times x squared minus x minus 6. How does that factor? Well, leading coefficient's 1, because it's a trinomial with a leading coefficient of 1. What multiplies to negative 6 that adds to negative 1? Well, negative 3 and positive 2. Times multiplies to negative 6, adds to negative 1. Good. Over x minus 2. So when I multiply these rational expressions together, I get x plus 2 and x plus 2. I get x plus 2 times x plus 2. You can change the order around any way you'd like. I get that in the numerator divided by x minus 3 times x minus 2. Because when we multiply rational expressions, we multiply across the top and then across the bottom. Well, there's a common factor of x minus 3, so goodbye. And then there's a common factor of x minus 2, so goodbye. So we're left with x plus 2 times x plus 2, which is better known as x plus 2 squared. You could write it as a trinomial, you could leave it as x plus 2 times x plus 2, but x plus 2 squared is the equivalent expression in lowest terms. Notice it didn't ask us to, but we should always keep in mind that x cannot equal 3 and x cannot equal 2, because that's when these two expressions are undefined. Number 2, again, we're multiplying these two expressions together, so our first goal is factor everything. So a squared plus 6a plus 9. It's a trinomial with a leading coefficient of 1. Multiply to 9, add to 6, that's 3 and 3. It's a perfect square there. A squared minus 9, that's the difference of perfect squares, a plus 3, a minus 3. Times 9 minus 3a, oh, there's a GCF of 3 there. Left with 3 minus a over a plus 3. Okay, so when I multiply these rational expressions, I multiply across the top, multiply across the bottom. 3 times a plus 3 times a plus 3 times 3 minus a over a plus 3 times a minus 3 times a plus 3. What are we left with? Those two divide to 1. A plus 3 and a plus 3, that also divides to 1, but here's where the little warning light goes off. 3 minus a and a minus 3, they do simplify, because I can factor out a negative 1 from 3 minus a, because that's a minus 3. If I factor out a negative 1 and use the commutative property, those two expressions are equivalent, so they do divide out, but I'm left with a negative 1. So I'm left with negative 1 times 3 is negative 3. So this is pretty cool because regardless of what number you plug in for a, you always end up with negative 3. I'd rather just say the answer that this expression always is negative 3 than plugging in a value and figuring out that you always get 3. Number 3, speaking of 3, number 3, multiply these together and express it in simplest terms. So hopefully you realize these are kind of just factoring exercises. You have to get quick at factoring and then dividing out like terms. That numerator is 4 terms, so I have to group. I group the first two, take out an x squared, and I get x minus 4. Group the next two, hopefully I can get an x minus 4. If I factor out a plus 6, all over what? Let's finish factoring that first before we move on. So that numerator is equivalent to x minus 4 times x squared plus 6. That's not the difference of perfect squares, so I'm not going to touch that. Divided by, what can I take out from the denominator here? Well, there's a GCF of x, and that leaves me with x minus 4. What can I take out from there? There's a GCF of x squared. I can take out an x squared, and I'm left with x plus 4. And then finally, that denominator, x cubed plus 64. Wait a minute, that's the sum of perfect cubes. That's x cubed plus 4 cubed. So that's equivalent to x plus 4 x squared plus minus, opposite sign there, minus 4x, always positive, 4 squared is 16. 4 squared is 16. So that denominator factors into x plus 4, x squared minus 4x plus 16. Sometimes you're going to have to go do scratch work on the side, and that's okay. That's okay if you have to go on the side and do some scratch work. So now that I've factored it, I'm going to multiply across the top and multiply across the bottom and get one big rational expression of x squared times x minus 4, x squared plus 6 times x plus 4 over x times x minus 4 times x plus 4 times x squared minus 4x plus 16. X squared divided by x, that leaves me with a factor of x. X minus 4 divided by x minus 4 is 1. X plus 4 divided by x plus 4 is 1. So I'm left with, in the numerator, I have x times x squared plus 6. In the denominator, I have that quadratic. And that's this rational expression in simplest simplest form. Is we factored everything, we multiplied them together, and then we divided out like factors. We divided out the like terms. Notice when I rewrote it, when I multiplied across the top, I used the commutative property of multiplication just to change the order of some terms. That's fine. You don't need to, though. So that's our final answer. Number 4. Number 4. Alrighty. So that's a trinomial with a leading coefficient that is not 1, so I need to use the AC method. What multiplies to negative 60, 6 times negative 10, that adds to negative 11. What adds to negative 60? That adds to negative 11. Well, what two numbers do that? What two numbers multiply to negative 60 that add to negative 11? Hopefully you said negative 15 and 4. So 6x squared minus 15x plus 4x minus 10. Take out a 3x from the first two terms. I get 2x minus 5. Hopefully I can take out a 2x minus 5 from over there. What do I need to factor out? A plus 2. So that numerator factors into 2x minus 5, 3x plus 2. So I know that numerator of that first rational expression is 2x minus 5 times 3x plus 2. Now we have to factor the denominator, and we get to do everyone's favorite game again, the AC method. We need to figure out what, I'm gonna make some room over here. What multiplies to a times c, what multiplies to negative 36, that adds to negative 5. What two numbers multiply, what are the factors of negative 36 that add to negative 5? Hopefully you said negative 4, negative 9, and positive 4. So we have 6x squared minus 9x plus 4x minus 6. Group the first two terms and we get 2x minus 3. So I need a 2x minus 3 from those two terms. So what do I need to factor out from those two? A plus 2. And I get 3x plus 2 times 2x minus 3. So the denominator factors into 3x plus 2 divided by 2x minus 3. Great, we factored the first rational expression. Now we get to factor the second one. Luckily, the numerator on this next one's nice and simple. I can factor out a 2, and I'm left with 3 minus 2x. Good. And finally, in case you didn't know how to do it already, we get to do the AC method on that denominator there. Hopefully you're looking at that and saying, that is written in a bizarre way. That's written in a bizarre way. That's really 4x squared minus 20x plus 25. Use the commutative property of addition to let you rearrange the terms there. Well, this is a trinomial with a leading coefficient that's not 1, so what multiplies to a times c, what multiplies to 100, that adds to negative 20. What two numbers multiply to 100 that adds to negative 20? Well, negative 10 and negative 10 do. So I have 4x squared minus 10x plus 25. From the first two terms, I can factor out a 2x minus 5. From these two terms, I'm going to factor out a negative 5, and I'm going to be left with 2x minus 5, so that I could group. So I get 2x minus 5 times 2x minus 5. So on the denominator here, I get 2x minus 5 times 2x minus 5. Now, maybe you're tired of writing this as one big fraction and just want to start simplifying things. Well, I have 3x plus 2 divided by 3x plus 2. Those divide to 1. I have a 2x minus 5 in the numerator and a 2x minus 5 in the denominator. Those divide to 1. What else do I have? That 2 is stuck there. 3 minus 2x, 2 minus 3x. Hopefully you're noticing that those look alike. They look alike, but I should probably factor out a negative 1. I should probably factor out a negative 1 from that expression and say this is negative 2 times if I factor out a negative 1, I get 2x minus 3. So I'm going to rewrite that numerator there by factoring out that negative 1. So those divide out. And what am I left with? What's my final answer? Well, when I multiply across the top, I get negative 2 over 2x minus 5. That's the final answer for number 4 there. Number 4, this was a lot of work. This was a lot of work, but hopefully you got practice at using the AC method and factoring trinomials whose leading coefficient's not 1. And as always, watch out for that negative 1. 3 minus 2x is divided by 2x minus 3. There's just leaving behind that factor of negative 1. Number 5, suppose that x equals that rational expression and y equals that rational expression. And we exclude 1, negative 1, 2, and negative 4 from the domain, because if you plug those values in, your denominator would be 0. So show that x squared y squared does not depend on the value of t. So even if you're not sure of what that means to show that it doesn't depend on the value of t, hopefully you said x squared y squared, I know how to compute that. I know how to compute that because that's x times x and y times y. Well, what's x? X is t squared plus 3t minus 4 over 3t squared minus 3. Since it's squared, I want to multiply it by itself. Times y squared. So I'm going to multiply y by itself. 2t squared minus 2t minus 4 divided by t squared plus 2t minus 8. So what we need to go through now and do is factor each part of these rational expressions. Really, I only have to factor 2 of them because the other 2 are just repeats. So let's look at this first one I just underlined in green. We have a trinomial up top, so that trinomial factors into t plus 4, t minus 1, because what multiplies to negative 4 that adds to 3, 4 and negative 1. Divided by 3 is my GCF, t squared minus 1. And hopefully you look at that and say, wait a minute, that's the difference of perfect squares. T squared minus 1 is t plus 1, t minus 1. And because this is x again, it's the same factors. It has the same factors, both the numerator and denominator. So there's the first 2 factored, and now we get to factor the next 2. The numerator looks like a trinomial with a leading coefficient, but there's a GCF of 2. If I factor out a 2, I'm left with t squared minus t minus 2. The denominator, before we factor the numerator more, let's factor the denominator. I get t minus t plus 4, t minus 2. What multiplies to negative 8 that adds to 2? 4 and negative 2. But if you look back up at the numerator, that trinomial can be factored, and now you don't have to go through the whole AC method because it now has a leading coefficient of 1. What multiplies to negative 2 that adds to negative 1? What multiplies to negative 2 that adds to negative 1? That's going to be t minus 2, t plus 1. And because this is also y, it factors the same way. Divided by t plus 4, t minus 2. That doesn't look like a t. t minus 2. So now that we factored this, we multiply across the top, we multiply across the bottom. But that would take forever to write that again. So I'm going to start canceling out my common factors right now. I have a factor of t plus 4 in the numerator. I also have a factor of t plus 4 in the denominator. Because these are all multiplied together, we can actually go through and do the division. I have a t minus 1 in the numerator, a t minus 1 in the denominator. Say goodbye to it. T plus 4, t plus 4. Notice how one's in the numerator, one's in the denominator. T minus 1, t minus 1. I have a factor of t minus 2 and another factor of t minus 2. I have a factor of t plus 1 and a factor of t plus 1. I have a factor of t minus 2 and a factor of t minus 2. These are all dividing to 1. They're not just canceling out. We just don't say goodbye to them. They're dividing to 1. T plus 1 divided by t plus 1. So what am I left with? When I multiply across the top, I get 2 times 2 is 4, over 3 times 3 is 9, so 4/9. Why does this show that x squared y squared does not depend on the value of t? Because regardless of what value for t you plug in, regardless for what value of t that you choose, x squared times y squared will always be 4/9. It's your choice. If you wanted to pick a value of t and then find x squared y squared, I can already tell you right now from doing all of this algebra that the answer will always be 4/9. So this shows why it does not depend on the value of t, because it's always 4/9. T could be 10, t could be 1,000,000. As long as t is not those numbers, x squared y squared exists and does not depend on the value of t. Maddie! Maddie was simplifying this expression and said the product is equivalent to x plus 5, when we exclude plus or minus 2 and negative 3. So that would be when the denominator equals 0. Explain what Maddie did wrong. So let's go through and do the simplifying and multiplication to see where she went wrong. I have the difference of perfect squares, 2 minus x, 2 plus x. Some of you are probably like, I put x plus 2 and x minus 2. That's not okay, because 4 is in the front seat here and x squared is in the back seat. So when I factor it, the number has to be in the front seat. Divided by x plus 2 times, that's a trinomial with a leading coefficient of 1, x plus 5, x plus 3, because those two numbers, 5 and 3, multiply to 15 and add to 8, x plus 3x minus 2, those numbers add to 1, multiply to negative 6. So now we can start simplifying. X plus 3 and x plus 3 divide to 1. Notice that 2 plus x is really x plus 2 because addition is commutative. X plus 2 and 2 plus x are really the same thing, so they divide to 1. But I have a 2 minus x and an x minus 2. Subtraction is not commutative. They divide each other out but leave behind a factor of negative 1. So when I multiply across the top, I have negative 1 times x plus 5. I have negative 1 times x plus 5. So what that means is that's what's equivalent to the expression Maddie was simplifying, not x plus 5. What did Maddie do wrong? Maddie did not leave behind a factor of negative 1 when she divided 2 minus x over x minus 2. That's in the form of a minus b over b minus a. If you picked numbers for a and b and typed this in your calculator, that quotient is always negative 1. So, what did Maddie do wrong? She forgot to leave behind a factor of negative 1. That was it for homework 2, for lesson 2 of unit 2.